If no, let's get into some discussion on what are your interesting problems and yes.
So there's a really interesting set of problems called internal ballistics for rocket motors.
Okay.
You have to solve for the burning surface of the propellant, which is a point mesh, and the properties of that mesh at every point, which are three-dimensionally space-dependent and time-dependent.
Would you like to come up and write kind of some kind of a simple description of a problem on the screen?
So you have some rocket motor, and inside of this rocket motor you have rocket fuel, and this rocket fuel is on fire along the surface, and that generates gases which go out the nozzle to produce thrust. And using Vieli's burn law, you can predict how much the propellant is burning.
Can you describe the variables you are writing?
So that's pressure, and then the A and N values are just empirically determined coefficients and exponents to make.
So A and N are constants.
Yeah.
And what is C?
PC. It's a subscript.
So what's the left-hand side?
Pressure. So burn rate. So regression rate. So this entire surface moves backwards by R every time step.
Okay.
And that generates some amount of gas, which creates a pressure, which feeds back into the equation.
Okay. So what's the equation for your pressure?
So pressure is Kn, so P equals Kn rho, and then there's gamma minus gamma. I don't remember exactly what it is, but it's some amount of gammas and minus gammas and to the power of.
Right, okay. So does anybody have any questions about the problem described over here? Yeah?
What is the ODE you're trying to solve?
So this is if you write this as like an X point, then this could be, or is there an eraser? This is X dot, if you will. Yeah.
Oh, so yeah, so it's like a D, like.
Yeah.
Or I guess R is like, yeah, it was a rate.
Yeah. My bad. Yeah.
I was going to ask, are you assuming constant pressure inside, or are you doing the internal flow simulation every time?
So you don't have to do the flow simulation. Well, you're supposed to, but you don't have to. This equation right here can calculate pressure on every time step, but pressure is not dependent on space in the motor.
Yeah, that's what I mean. Constant pressure in space.
Yeah, so that's actually
it's different every time step, but the same at any point on your mesh.
It's a relatively okay assumption for most rocket motors to say that pressure is constant inside the motor. It assumes that you have a short rocket motor so that there's not much flow velocity because it's actually static pressure, not stagnation pressure. So that can lead to sadness, but...
Oh, that only works with static pressure? That's interesting.
Yeah.
And so is the PC a function of X?
No. So PC this just substitutes right in there. So you only have a single equation, right? So you've got...
Yeah, but like, does it depend on X?
No, it doesn't. No, it does not. dt equals...
Why can't you solve it analytically?
Because the interesting case of this is when it gets more complicated and P is dependent on X. And where X is also dependent on a like Y coordinate along the motor.
Oh, yeah, that'd be interesting. So if you have instead of a flat slab of fuel, you have like an angled slab.
Well, so it might even start as a flat slab of fuel, and it turns into an angled slab of fuel, because the burn rate doesn't have to be constant along the motor.
That according to this equation, this can only happen if the pressure is not constant in X.
So you can add a term where you've got flow velocity, but
Okay.
I'm not sure how complicated you wanted the example to be.
Okay. Right. So the first question would be, would this be a stiff problem or non-stiff problem?
Probably not stiff.
Yeah, it doesn't have that vectors, but of different types.
Right. So let's first analyze what are the time scale, what are the effects in the system, right? What are the time scales in the system?
Oh, you know, it might be if you end up with the flow velocity addition, it could become stiff because the burn rates are like the things to do with burning, like pressure, like the pressure transitions and things are probably going to be fast, but like the flow velocity might change with time relatively slowly.
Well, let's first figure out what are the state variables in here, right? So when you want to describe a system using ODEs, you need to say d state variables dt equal to a known function of these state variables.
Well, in this case, it's just x, right?
It's x.
Yes.
So the time derivative of x can be represented as a known function of just x.
Wait,
So-
just x or just pressure?
Pressure, which is
So then pressure is not something is pressure something you know?
pressure can be calculated by knowing dx dt.
Oh yeah.
Not knowing x.
Not knowing x, yeah, it's not dependent on x, it's dependent on dx dt.
It's depend on dx dt. So that's
correct.
actually not. So you can't write it as a function of x.
No.
Okay. So x cannot be just the state variable cannot just be x.
So the state variable would have to be x in the first derivative of x.
So would that work if so can you write it down? So if the state variable is x and the first derivative of x, what equation would you have?
So how do I write that? Dx dt equals a. I don't actually remember the equation for PC, but PC is a function of x dot.
I see.
I'm mixing notations again. Dx.
Okay, so can you plug the second equation into the first one?
Yeah.
Dx dt, right?
Yeah.
Dx dt over dt. Yeah. Okay. So good. Looks like you have a analytical form of PC, I guess. Okay. So this equation is actually very interesting. It has time derivative in it. It's obviously an ODE, but it's not an ODE we wrote down in our class, right? So how would you solve an equation like that?
It's a normal equation.
So okay, the PC also doesn't depend on.
Like in this case, the dx dt is constant.
You have a very good observation.
So
This is actually
no,
not
it's-
an OD
No,
at
it's
all.
not, because I did a poor job explaining, because there's a kn function
Okay.
that does depend on x, I guess. So kn is the ratio of surface of x
Uh-huh.
to this area right there.
I see. So KC goes into which function?
Uh,
Where is kt?
so kn. So if you assume this is a cylinder, right?
Yeah. Okay.
Where x is like defined from here,
Okay.
where this is 0.
Okay.
Then your area is
Yeah, I
pi.
mean like this Kn, how does it go into
How does
this
it play into
equation?
the
Yeah,
dx?
where is the kn inside the ODE?
So PC. Do you just want me to Google the equation so I get it right?
Sure.
Or PC is some function of Kn
And dx dt.
and dx dt.
Okay.
So it's actually comes from
Okay,
the
I can.
back
Yeah, if you can Google this equation, I can take it from here. Right. So this is a very interesting case because what you have is dx dt equal to a function of of x and dx dt. So rho c is a function of kn, which is a function of x, and the dx dt. All right.